Great. Well, while I'm talking, I can't see anybody, so it's very strange. It's like I'm talking to a screen, but I just wanted to take just a couple of minutes to introduce the work itself, and then I'll hand it over to Kris primarily to do a presentation, and then we'll have the opportunity to ask questions about this work. And first, I just wanted to say thank you to Raquel, Kimberly, and Tess for supporting these lunch and learns and inviting us here today. It's a huge amount of work that we've done. I'm personally very proud of it, and proud to have worked with the team to get us here. And like Michael said, this is a very unique partnership that we've developed over the years. And I dare say that we started this conversation about a decade ago. And it took that long to get us to this point. And I wanted to just explain a little bit of what it took to get us here. So this work was a collaboration between the SFPUC, the Port of San Francisco, the SFO, and our Office of Resilience. And we are the lead agency pulling this work together. And how did we get started? Well, primarily under SFPUC, we were doing a element of that program that was looking at climate change. And that's where I started my relationship and professional relationship with Kris, and a little bit later with Michael. And the first thing that we did is we developed sea level rise vulnerability mapping. That was a really big lift for the city, and it was one of the first data sets that launched the city to be able to really start thinking about and working on planning for sea level rise. As we were working on that, the city was also preparing a sea level rise action plan that was done through the SF Planning Department. And when that was completed in 2016, we identified extreme precipitation as a critical data gap. We understood that to be a data gap, and we were already in conversations with Michael and Kris, looking at how across the country, across the globe, Michael mentioned the IPCC, and we wanted to understand how could we in San Francisco and the Bay Area get a better understanding of extreme precipitation. One of the ideas was to do downscaling of the global models that have been produced for the IPCC. And we really realized that that information and the scaling of that wasn't really going to work for San Francisco. We're very unique here in terms of how the positioning of the city next to the ocean, very, very hilly. And so we wanted to really look at a different option, and that's how we began the relationship with Michael. And it took a number of years. It wasn't until 2019 that we actually initiated the work. It's been an incredible amount of work with countless hours of computer modeling. And when I say computer modeling, think of an entire building filled with computers. And that's what it took to analyze this information. We started with storm selection with our partner agencies. We picked 4, 5 storms. I can't remember exactly how many, and looked at those storms, which storms were creating flooding problems for us in the past. And from there, we would do our work. And so first we selected those storms, and then LBNL went to work. They had to take those storms and develop the modeling that would recreate those storms and what they looked like. Like I said, a huge lift. After we did that, we then applied what the future conditions would be. We looked at the greenhouse gas emissions and the different scenarios that we could consider. And we're following along what we've done with sea level rise, looking at a no change scenario for the future. So we could really see what's the worst case scenario. And we applied that information to those storms. And that's what gave us the data results. And then we moved into analyzing that data as a Herculean lift for Kris's team. And from there, we've been developing documents that describe all that work and the tools that are coming out of it. Just some really big key takeaways. Not surprisingly, extreme storms are going to drop more rain in a shorter period of time. The thing that was very surprising to us, and we weren't really prepared for, but that's what the science is showing us, and you'll hear a lot more about this from Kris and Michael, is that the smaller storms are also increasing. They're even increasing faster and larger than the extreme storms. So that's the storms that for us at the PUC, our 5-year, 3-hour storm, what we manage through our system, that's going to get much larger. And so again, one of our key takeaways is the PUC wastewater system, we're not going to be able to manage those changes alone. We took all of this information and we started having the conversations with our partner agencies all the way up to the Capital Planning Committee. We started preparing high-level recommendations. There's still a lot of work to do with all of this data that's coming in. And some of those are, we need to develop a flood resiliency policy, not just a statement, but a policy itself for the city and county of San Francisco. PUC is going to champion that, but we're working with our partner agencies to lift that policy up. We've started that process. It's likely going to be a couple of years to get that all the way through and complete. But some of the other things that are really important, and you'll also be hearing about, is that we need to integrate these results, this data tool set, with the other climate-related data sets, sea level rise, shallow groundwater, and other elements that we're utilizing. We want to expand department participation in the climate resilience program. That's actually been more called Climate SF. That's where the city agencies are all coming to the table and talking about what are we individually and then collectively doing to plan for and be prepared or help prepare the city and county of San Francisco for climate. We think we need to refine our decision-making process. We're no longer necessarily one agency doing a project. These climate change related projects are going to require multi-agency participation. And then lastly, we need to think about how we're going to finance this. This stuff is going to be extremely expensive for the city. So we need to really start thinking about a cross-department climate change financial plan. So those are some of the things that we're thinking about in terms of the city. That's how we got here. But I really want to hand it over to Kris and Michael. They're the scientists, and let them share their information and be here for Q&A at the completion of this. So thank you.
Thank you, Anna. Let me get my screen shared. Oops, wrong. Let me flip it. All right. Now you guys can see my screen, I hope. So I'm going to talk a little bit about this amazing study that we have been working on for many years, starting the work in earnest in 2019, as Anna said, and we've been calling it the Extreme Precipitation Study, but it's really about much more than just extreme precipitation. And it's taken a lot of people to do this work. Several folks from my team at Pathways Climate Institute. Michael Wehner has been probably just an instrumental influence throughout this project. But Christina Patricola, who once was working with Michael at LBNL, she's the one that led a lot of that numerical modeling on those supercomputers. And she is now a professor at Iowa State University, but has stayed engaged with us on the progress on this study. We are nearing the finish line. I think all of the work is done. And we have 2 reports that are coming out. We're going to finalize them at the end of this week, and then they should be released for people to look at, hopefully very soon. So we split it up into 2 volumes. Volume 1 is really focusing on some of the bigger picture of the science, and we're really tailoring that towards decision makers. So making it really accessible in some plain language. And then Volume 2 is where we're actually providing tools and data that the stakeholder agencies have requested. So the PUC and the Port and SFO in particular. And so Volume 2 is definitely more of a technical document. So that's one of the reasons we've split them into 2. And we've been focusing on these storm types like you can see on the screen. I'm sure many of you have seen tons of satellite images of atmospheric rivers and extratropical cyclones on TV lately as we've gone through this winter season. This particular picture is of the October 2021 bomb cyclone that impacted us in the Bay Area in 2021. But these are the type of storms that we have been looking at. So why is this important and why did we, lead this study? Yes, it was definitely identified as a data gap in 2016, but we had been looking at ways to better understand how these extreme storms were going to change in a warmer climate, even before like the presentation of that action plan. I think there's a huge desire to like be better prepared for future storms. And we need to include this information in future long-range planning, design, and implementation. And so these are like some news headlines from what we saw in 2021. If you can remember all the way back to 2021, the huge storm that hit us in October like took everybody by surprise. That was the size of a storm hitting in October that we like hadn't seen before, but it was just one storm. It's very different than what we're seeing this winter being hit by like back-to-back storms. I think these terms, atmospheric rivers, extratropical cyclones, and bomb cyclones have like really integrated through a lot of different people's vocabulary this winter, which has been really great to see. I will say we're not going to answer all of the questions on how we're going to use this information in this presentation or in this study, but we're giving you all of the great tools that the city needs to start getting prepared. So volume 1, as I mentioned, is really focusing on the state of the science targeted towards decision makers. It provides you an overview of the latest advancements in climate science, talking about the type of storms that impact the Bay Area with a focus on extreme precipitation in the Bay Area. It goes over the details of the future storm modeling that Anna mentioned, but it really tries to hammer home some of those big findings, which I'll mention a little bit more in a minute. And then volume 2 gives us a little recap of volume 1 in case you didn't read it. It goes over in a lot more detail the storms that impacted us in 2021 and these winter storms of 2022 and 2023. And then it goes into the methodology of how to create these future condition, intensity, duration, frequency curves. And I'm going to talk a little bit more about those in case you're not familiar with IDF curves. And it presents future condition IDF curves for San Francisco and also the San Francisco airport. Those were the primary outcomes that we wanted to create for the city. We did all of this looking at the worst case scenario that the IPCC models, but we provide information in this guidebook that people can scale these IDF curves to really look at any climate scenario to support risk-based decision-making, which is really important. We had to look at the worst case so that, the mathematic works out and we're scaling down. So most of the results I'm going to present today focus on that worst case scenario, but I'm an optimist and the goal is that we're going to do enough as a global community that this worst case scenario does not become the reality for my children, my children's children, and the rest of the world. So the first thing to understand is Bay Area storm types. And a good thing to know is that extratropical cyclones and atmospheric rivers are not just associated with extreme storms. These are the storms that bring the rain to California. Like, this is it. And extratropical cyclones can bring cloudy days and mild showers, or they can bring heavy precipitation, thunderstorms, blizzards, all that heavy snowfall that we've been seeing this winter. Atmospheric rivers, the same thing. These originate in the tropics and bring the rain to our area, to the West Coast. They actually have atmospheric rivers all over the country. But these as well can bring that light, beneficial rain that helps keep things a little bit green, helps us prevent more drought when it's light. Or these can bring those torrential downpours and high winds, like the storms that we've been having this winter. It's challenging because in the media, they usually only use these terms when it's a really big hazardous storm. But I want you to understand that ETCs and ARs, those are our two common storm types that impact us in the Bay Area. Each of these storms can happen on their own, but they can also happen in combination. And having them happen in combination is actually the most common storm type we see. It's what we have been seeing this winter. And then ETCs can go through this rapid pressure drop, and they undergo something that's called explosive cyclogenesis. They become even more powerful with more powerful winds. And we've been seeing that this winter. When you hear about a bomb cyclone, that's what we're getting. We're getting that ETC that is becoming a bomb cyclone, and it may be coupled with an atmospheric river, making both of them stronger as well. Well, that's kind of an important background. The modeling, I'm not going to go into detail on all of the amazing modeling that LBNL did, but what we did was we used an approach that's called a story approach. It helps us tell a story. So we identified a whole series of historical storms going back to 1980. We looked at storms that really impacted San Francisco and SFO. Those were our big storms of interest. And then LBNL modeled those storms under historical conditions. So modeled them as they happened in the past. And then once we were comfortable that we're getting all of those storms modeled correctly, then those storms were modeled under a warming climate in the future. So if that storm happened in 2050, when the world was, 2 degrees Celsius warmer, what would that storm look like? And then we modeled it all the way into the future of 2100, under that worst case, when the world could be 4 to 5 degrees warmer, what would that storm look like? So we could really understand how climate change is going to change the way these storms behave over the Bay Area. I want to note that we have to date just looked at how these storms are going to change. We have not looked in detail on what the impacts on the ground are going to be for San Francisco and San Francisco's sewer system and the infrastructure, although we're getting a preview of some of that through these winter storms. But we have not yet modeled what this is going to do to the combined sewer system. What could the flooding look like in light of this new information? All of those kind of details are yet to come. But the big findings, some of which Anna talked about at the beginning, is that extreme storms are going to get bigger. And when I say extreme storms, I mean everything from the 1 year to the 500-year storm. Those are the storms that we looked at, and those are all going to get bigger. They're going to have more rainfall. The storm itself is going to have a longer duration. So maybe instead of 2 days, it's going to be over us for 2.5 days by 2050, helping to bring that more rain. And then they're also going to increase in AR category, so atmospheric categories. So most people are familiar that hurricanes are rated based on a category like Cat 1 or Cat 5. Cat 5 is a really strong, bad, damaging hurricane. We have that same category system for atmospheric rivers. It includes atmospheric rivers coupled with ETCs. They all go in there together. And so atmospheric rivers that are a 1, that's a beneficial one that's probably not going to make the media, but categories 4 and 5 are the more hazardous type. And so we looked at how these storms in a warmer climate, how would that AR category change? And we're seeing that they get bigger. All right, so I'm going to talk a lot about intensity, duration, and frequency without going into a lot of detail on the curves. I have to talk about these concepts, so that I'm just going to define them up front, just in case anybody isn't familiar with intensity, duration, and frequency curves. Precipitation is hugely complex, and so we can't it's a multi-dimensional problem. And so for the most part, we break it down into these three things: intensity, how much rainfall will fall, how many inches; duration, over what duration is it going to fall, how many minutes, how many hours, how many days; and then frequency, how often is that amount of rainfall going to occur. And one storm is going to be filled with lots of periods of lots of different combinations of intensity, duration, and frequency. So when we combine them all together, we're not talking about one single event. We're often talking about one piece of one storm. So I'm going to talk about it in terms of like intensity, that's how many inches of rain; duration, how many hours; frequency is like, this is the 5-year. So a 5-year, 3-hour event that could produce 1.3 inches of rain, that's using these terms: intensity, duration, and frequency. So this is what an IDF curve could look like. This is for storms with a duration of 24 hours. And then on the y-axis, we have rainfall depth in inches. And then on the x-axis, we have return period. So we're going from that 1-year storm, that annual storm, all the way up to a 500-year event. And so the black line is showing that's historical. If we look in the past, that's the curve that storms took. The blue line is 2050 and the orange line is 2100. And then they each have what we're calling their own 90% confidence interval around that value. And so this is kind of an important thing to take into account. And then this is also, again, using that worst case scenario from IPCC. This graph looks very similar to how we look at like sea level rise projections, but it's just a little more complicated because we have multi-dimensions. So if we look at this in terms of some of the numbers, what we see is if we look at the 5-year 24-hour storm, we can see that under historical conditions, this is producing 1.3 inches of rain. But by 2050, the amount of rain that's going to fall is going to increase by 17%. And then by 2100, the amount of rain that's going to fall could increase by up to 41%. So that's a big increase in rain. And then if we look at the 100-year 24-hour change, we see bigger increases. And so there we're going from about 5.8 inches of rain historically. By 2050, those are going to have 22% more rain. By 2100, 51% more rain. The storms that fall this winter, those are already like in this band of, I think Michael had estimated we're already seeing like a 5% increase today based on the amount of climate change that has occurred. So we're already on this track towards 2050. That 0 point doesn't start today. I know some people, when we're presenting these numbers, are like, well, it's 17, but it's +2 to +27. That's a really big confidence interval. How confident are you in these numbers? And that's why I've included the historical numbers on this slide, because even with our historical numbers, it's just the nature of statistics that you have this 90% confidence interval. We just don't usually talk about it with the historic numbers. But we have like a range of -10 to +13 on these historical numbers. So the confidence intervals are really in line with our analysis of historical storms. And then of course, as we go over time and get farther out into the future, that 90% confidence interval just increases. But these are some big changes. We can also look now, instead of looking at that 24-hour duration, that 24-hour duration is like really important for like overland conveyance. We can look at that 3-hour duration. This is what's more important for like the sewer infrastructure. These the amount of rain that can fall during 3 hours is actually increasing more than the amount of rain that could fall over 24 hours. So by 2050, like the 5-year 3-hour storm could be bringing 20% more rainfall. And by 2100, 56% more rainfall. So those are big increases in how much rain could fall during that 3-hour duration. And then the same with the 100-year 3-hour storm, it's increasing even more. By 2100, the 100-year 3-hour storm could have 67% more rainfall and even up to 87% if you look at that confidence interval. This was a really huge finding from this study because most studies don't actually look at the shorter durations, and we ended up looking down to like 15-minute durations. But to have these shorter durations have like more rain falling, that has big implications for flash flooding, for sewer conveyance, for potential damage and life safety issues. And so this was definitely one of our big findings from the study, and we are already seeing this dynamic when we look at the winter storms. And San Francisco is not alone in seeing this dynamic. While we were wrapping up this study, there was a great paper that Michael Wehner brought to our attention from Australia, published in 2022, that they were also seeing increases in that sub-hourly heavy rainfall. And so I'd just like to highlight some of the things that they put in this little abstract. These are directly relevant to us in San Francisco. Potentially that shorter duration extreme rainfall, that is the thing that can cause flash flooding and threaten life and infrastructure. So we really need to pay attention to these differences. As I noted, previous studies, even studies like the one we're doing, they usually focus on daily totals and not 3-hour, not 15-minute. So these are really critical findings that are really important, and we only have them because of this study that we have done. It's already happening now. We're already seeing these increases in the shorter period. The storm that happened from December 31st to January 1st, the really big one that hit us, the amount of rain that fell in a 3-hour period was like a 300 to 500 year rainfall event. So it had a huge increase associated with us. So we need to pay attention. Excuse me. Let me take a sip of water. So I also want to talk about how these AR categories are going to change, because I mentioned that. And this is important because it's another, I think, looking at the AR categories is a way to communicate the differences that more people might be able to understand. Not that I would love it if everyone understood IDF curves, but it doesn't resonate with everyone. But I think AR categories can resonate with the public as well as decision makers. So there's 5 current AR categories on this scale that they range from category 1, primary beneficial, to category 5, primarily hazardous. I think most of the ones that we've been having this winter have been like on the range between Cat 3 and Cat 5. The media does a lot of us, I think, a disservice is that you're not going to hear it on the news that it's a category 1 atmospheric river, because that's probably just some light beneficial rain. So it doesn't make a lot of the media attention, but really all of the rain we get can be bucketed in these different categories. So one of the storms that we looked at was an atmospheric river only. And this is a storm that occurred from January 3rd to the 5th in 1982. This was a very short duration storm, but very strong in magnitude, delivering heavy rainfall across the Bay Area, concurrently with very high tides, which really exacerbated the amount of flooding. In San Francisco, 4.7 inches of rainfall was recorded within 24 hours during the storm, so a lot of rain. And in San Francisco, they recorded 5.6 inches of rainfall. So this is a storm that actually hit SFO harder than the SF downtown gauge. When I talk about San Francisco, we're usually looking at that San Francisco downtown gauge. Under historical conditions, so under this one over here, what was hitting San Francisco was primarily a Category 3. So a mix between hazardous and beneficial, but definitely a lot of rain. It could still most likely be a Category 3 by 2050, although the Category 3 spreads farther inland as the storm is making landfall. But by 2100, we'll actually see changes where this storm starts moving into Category 4 over, many areas of the Bay Area, San Francisco, and the Northern Bay Area, where it's turning into a Category 4. Some areas that could be Category 5, but that's before it's making landfall. So this is actually changing that AR category and helping us understand how much more damaging this storm could be in the future. So now this is another storm that we looked at, one of the ones we modeled. This storm happened December 10th to the 15th in 1995. This one was an AR plus an ETC, and it had a significantly huge bomb cyclone. So this was a different type of event than an AR only. We actually see the most significant, biggest changes when we have this AR ETC combination. But this storm, when it occurred, if anyone remembers it, I remember it up in Washington because that's where I lived at the time. This storm was considered the strongest winter storm of the previous 70 years when it happened. And it hit from Central California all the way up into Lower Canada. These storms are big. We had extremely heavy rainfall, peak winds of over 80 miles per hour. And in one day, over 1,000 trees fell over in Golden Gate Park alone. So this one caused a lot of downed trees, power outages, which, as you can see, when we look at it under historical condition, this one was really powerful. This was a Category 5 AR, which is our highest category on the AR scale. Like, this was a bad storm for us. But as the climate gets warmer, 2050, this could be a Category 7 for San Francisco. And Category 7 isn't even on the scale. By 2100, under a warmer climate, this could be a Category 8 for the Bay Area. So what we're seeing as the climate is getting warmer, we may have to add new categories to this AR scale to describe how destructive and damaging they could be, which is a little scary, but now we know we can start getting better prepared. One thing I'm asked a lot is that, wow, well, you're saying everything is going to increase. We're going to get more rain. It's going to be longer. It's going to be more damaging. Does this mean we don't have to worry as much about the drought? And the answer is no. We're still going to have a lot of periods with prolonged drought. Our climate is just going to continue to flip between extremes, and the extremes are probably going to be more extreme than what we had historically. We're still going to have long periods of below average rainfall, so drought conditions, interspersed with really extreme wet years, like what we're having now, or what we saw in 1997, or what we saw in 1983. Those are kind of our two biggest comparable years to what we're seeing this year. Although those were El Nino, this is La Nina. So the strength of these storms is still kind of being discussed by a lot of scientists, including Michael, who's with us today. So in October 2021, we had a huge bomb cyclone that was really a significant event all in and of itself. It made national headlines, but it was just one big storm. So it didn't do a lot to change drought conditions. But this winter, we're having record-breaking rainfall and snow. We have had like 13 storm systems to date since end of December, which is like a lot. It's raining right now. We have 2 more storms on the way. And so the continued presence of these storms and the rainfall has brought some drought relief. Of course, it's also creating a lot of other problems and flooding problems that could continue well into the summer as the snowpack melts. So there's still a lot more to come with this storm season. And then drought conditions will likely return at some point in the not too distant future. So this is kind of nearing the end of my presentation, and hopefully I've left enough time for questions, but I just want to say this is a huge problem and it's a really scary problem, but that's exactly why we did this study. We wanted to understand how big these storms could get, and now we know. And it is much easier to plan for the known rather than the unknown. And if we can stay off that worst case climate scenario, then ultimately it hopefully will not be as bad as some of the information that I've shown you today. And with that, I thank you for letting me talk all about this study, and I will stop sharing my screen so we can take some questions.
Well, before we do that, Kris, I just want to say thank you again, and I'm going to take a deep breath here and let everybody else take a little bit of a deep breath. It's a lot of information, extremely technical, scary. But the good news is that we didn't do this in a vacuum. We're working with global leaders on the science. We're collaborating with our colleagues across the United States. And in fact, working with the Water Utility Climate Alliance, the stormwater sides of those businesses, this work is being held up as a, what other folks should be doing for their systems. So we're leading in this regard. And as Kris said, it's scary, but at least we have the information and we can start making pragmatic, financially important decisions for the city. So I'm just going to pause there, and before we go into the Q&A, I just want to give Michael an opportunity if you want to share anything at this point before we start into some Q&A.
Sure. Thank you, Kris, for an excellent summary of our project. I answered some of the Q&As. There's one I don't want to answer. I want Kris to, but I do think that it's important to repeat what the aim of this activity was. It was not to try to predict changes in available water for the water system. I know that some of the people online are probably interested in that question, but rather it was to try to get a handle on these disastrous storms. When infrastructure is overwhelmed and those kind of immediate impacts of floods, for instance. And so I hope that's clear. I tried to answer some of the questions about changes in the seasonal total. I think the most relevant piece of information is about what Kris was talking about in the drought. We will still have droughts. In fact, we'll have drought years with big storms in them that provide all sorts of problems. And in fact, there is some evidence that the year-to-year variability has already increased in California and will continue to. So just to be clear about what we were trying to do here, it's not to answer all the questions about rain, but just these ones about severe storms that are impacting the city rather directly.
Thank you, Michael.
Thank you so much, guys. That's a very helpful information. I've learned a lot so much about your presentation, Anna, Kris, and Michael. And so first, I have a couple of questions first before we move to our Q&A. Anna, how did you come up with your current position as far as education and career path?
I touched a little bit on that in the beginning. So I have a science degree and have been doing environmental focused work since I graduated from college, and also as a Peace Corps volunteer. But I've been in the field of environmental work for many years.
Excellent. Thank you.
Yeah, like 25 years.
Yeah, no wonder your presentation is amazing, Anna. So
Thank you.
let's move over to Raquel for some of the Q&A from our audience.
Thank you, Tess. Thank you, Michael, for answering some of the questions that came in via the chat. We have a couple of more, and I'm going to just dive right in. On a high level, how does the increase in temperature in your models change the historical storms?
I'm typing that one right now.
Well, why don't you answer it for
Yeah,
our
okay.
friends in the audience who aren't
Yeah.
reading the Q&A?
So in two ways. The first is we know that in a fully saturated atmosphere, so when it's raining, when relative humidity is 100%, that the actual amount of water increases by about 7% per degree centigrade of local warming. And so this is something called the Clausius-Clapeyron relationship. It was invented in the 19th century to make steam engines more efficient. So it's not rocket science, it's steam engine science. And if you look, this actually kind of gets to why we did this study, because if you use that thermodynamic relationship alone, you would say, well, these storms are only going to be 7% wetter for each degree of warming. And, prior to actually Hurricane Harvey, which, pardon the pun, was the watershed moment for this, I would have believed that. In fact, I was on the record for that. But what we've learned since, by looking at these storms rather in detail individually, is that there's more going on, that there is this available water, but the storms are increasing available water, but the storms are more efficient at raining that out. And that's why these numbers are so big, because they have more water and they're more intense, and because of the increase in energy. And we learned a lot about hurricanes through Hurricane Harvey and subsequent studies. Now we're learning the same about atmospheric rivers and extratropical cyclones, and perhaps surprisingly, because they're very different kinds of storms, the results are similar in that that it's worse than I would have expected or even said 10 years ago. I'll finish typing though. So.
Got it. Thank you, Michael. Okay, so Kris, I believe this one Michael was holding out for you. Does the report cover the upcountry area where the city and county of San Francisco has their water storage reservoirs, like Hetch Hetchy and such?
The report does not extend our results really outside of the Bay Area. I think our model domain does extend there, but we were really focused on these like 5 extreme storms that were modeled. And so I think as Michael had mentioned, the results of this work, I don't think quite extends to the type of answers that are needed for the water supply side. But they could help inform some of that increase in snow that we've seen this year. I think, yeah, it's been a record snowfall year up in the Sierras.
Yeah, the domains do include the Sierra, sort of by design. We wanted to know, we felt it was important to have that in there, and it wasn't all that much more computationally expensive. But and it would be interesting to go back to those and look at the fraction of snow versus rain. One of the things I answered in a previous question was that kind of obvious, as it gets warmer, the fraction of precipitation that falls as snow will decrease. And my colleague Alan Rhodes at Berkeley Lab who's a real mountain climatology expert, has written a number of papers that suggest that under this worst case scenario, there would be no snow in the Sierra in February of 2100, for instance, in this warmer scenario. And even at the middle of the century, there's something like half as much. And this is a really big concern to me, because we use the Sierra snowpack as a temporary reservoir, as many of you are well aware. And if we lose that, what are we going to do? And we have a whole system in California to exploit the seasonality of when things melt. And there is a lot of evidence that already the snow melt is earlier in the year than it traditionally had been. And so, how do we adapt to that? That's a question for those experts.
Raquel, if I could just jump in, just a sort of a reiteration of what we've already been saying, but this work was really done to support rain management in the San Francisco area. We weren't really looking at drought per se, but you may want to reach out to David Bihar on the water side of the business and ask if he has a presentation he'd like to share with us. I know he's been doing a lot of work on droughts. What does it mean for water supply? Going through some of the same scientific analyses of what should we be expecting in terms of storms, snow, all of those elements. I would say in terms of the work that we've done, we can use some of this information to not look at drought conditions per se, but how does it affect our local reservoirs? I know that I talked to some folks on the water side of the business, and these last storms, these big storms, it was raining just a little while ago, created a lot of turbidity problems with the water system. It could also overwhelm our dams, the infrastructure that's holding that water back. So there's all types of elements of criticality that we could think about and catapult off of this information to other elements of our of the SFPUC.
Got it. Thank you, Anna. Okay, with just a few minutes left, I think we'll go over maybe one or two questions, one more question or so. And perhaps after I can coordinate with you all to answer the questions that we don't get to today. So with respect to the strength and duration of a storm, is there a recommendation on what to prioritize? Damage control, collection system, water treatment, etc.?
I mean, I think at this point in the study, we haven't been able to develop recommendations for the city like that. But I would say all of the above in these storms are really going to be needed. There's not going to be a time when we can take these size of storms, even the storms we're having this winter, and safely convey them all through the sewers. And so we're going to need innovative solutions to kind of safely convey floodwaters out of the city, ways to potentially store and detain some of that water. Yeah, it's going to be we need a lot of innovation and a lot of discussions to see how we can help the city better prepare.
Raquel, I'll just add to that too, that we're back to that citywide effort and looking at climate change. We're partnering with the port along with our other sister agencies, looking at ways to protect the city from sea level rise. I saw a question in the Q&A about sea level rise. So one of the reasons this work is so important is that the port is looking at ways to keep sea level rise out of the city. If we do a really good job there and we're keeping water out, that also means we're keeping water in. So if we're having deluges of storms, we could be creating other problems related to flooding. So that's those data sets, you start layering them on. And as Kris said, it's all of the above. These are not going to be easy things to think through. But that's why this information is so important across the city agencies.
Got it. Thank you. We may have time to cover one more. Do you have an estimate of how many inches of sea level will rise in the Bay Area in the next 10, 20, or 30 years?
I mean, over the next 30 years, or really, yeah, maybe less than that, we're going to see at least a foot of sea level rise. And we're pretty certain on that. The federal government actually released a report in 2022 that had a lot of great information on sea level rise. And they were able to model the tide gauges and the satellite data and get a really high confident extrapolation out to the next 30 years. And they're going to be kind of updating that every 5. And as part of this extreme precipitation study, we're going to be providing guidance on how that we should pair this extreme precip information with sea level rise information. So we're doing apples to apples with the amount of warming It's not included in these volumes right now. Kind of got stripped out in the editing process, but that will be available. So we make sure that people are considering kind of the confluence of climate impacts.
Got it.
The key words there that Kris said were at least.
Yeah.
This is that's you know, the lower bound on this estimate, and there is a great deal of uncertainty in sea level rise that's tied to the stability of the West Antarctic ice sheet. And there is recent work that suggests it's less stable than we had hoped.
Got it. Thank you, Michael. So it's 1 o'clock now. We have a couple more questions that we will cover offline, and I'll be sure to send the responses out to everyone. I want to thank you again, Kris, Anna, and Michael, and Tess for presenting today and helping us host the Lunch and Learn. And with that, we'll see you all next month. Take care, everyone.
Thank you all.
Thanks, everybody.
Bye-bye.